This video is a short summary of some of the properties of dissolved oxygen and its relationship with water quality. Dissolved oxygen, O2 aqueous, is one of the most important chemical constituents of water. If there's no oxygen in the water at all, everything dies, except for those hardcore chemoautotrophs living in totally anoxic conditions. If it's so crucial to the survival of life underwater, how does it get there? More importantly, how does it stay there? Generally speaking, O2 enters the water in one of two ways: through diffusion and through photosynthesis. Oxygen can diffuse into water by aeration. If the water gets churned up enough, like at the base of a waterfall or over rapids, there's a better chance some of the O2 being forced under will stay down there and become aqueous. Oxygen can also enter waterways through photosynthesis. The reconstruction of CO2 and H2O by plants, both terrestrial and aquatic, creates a sugar, usually glucose, and lots of O2 as a byproduct. When this takes place underwater, some of the O2 being released by the aquatic plant dissolves in the water instead of bubbling to the surface. So, if you can't get your hands on a pond aerator, make sure you have some aquatic plants in there, or your tadpoles won't last very long. Now let's talk solubility. Firstly, cold water can hold more O2 than warm water. The H2O molecules in warmer water are too agitated to keep it dissolved, and the solubility of any gas in water is inversely proportional to the water's temperature. Secondly, flowing water always has more dissolved oxygen than stagnant water. That way, the O2 can't be consumed by bacteria decomposing organic matter. And finally, fresh water has a higher O2 saturation capacity than salt water. In healthy terrestrial systems, O2 makes up around 21% of the air composition, or 210,000 parts per million. In healthy aquatic systems, dissolved oxygen sits at around 7 to 14 parts per million, a very narrow buffer zone which makes the overall health of the underwater systems very precarious and extremely sensitive to O2 depletion. Low O2 also affects redox potential in the water system, and it can also diffuse into the sediments of waterways, which, if they contain a lot of decomposing organic matter, also contribute to low O2. Essentially, a water system is healthy when its O2 production is greater than its O2 consumption, i.e. the supply is greater than the demand. So, what in the water system demands O2? Well, O2 is not only an electron acceptor, but an electron grabber. So it is demanded by basically anything that is an electron donor, especially reduced molecules. For instance, bacteria decomposing organic matter release elements and compounds with electrons to spare, so O2 is only too happy to latch on. Anything that respires, including plants, needs the O2 to burn sugar for energy, so both can be reformed into CO2 and H2O, thus completing the photosynthesis respiration cycle. In short, dissolved oxygen is an important measure for water quality due to how critical it is for the survival of complex aerobic aquatic life. There are several ways for it to enter and leave the water column, and surprisingly, O2 doesn't seem to want to stay in the water column, and it doesn't take much for it to leave if the water conditions don't meet its standards. That was a little summary of O2 and its relationship with water quality. Thanks for watching, and happy learning.